So this material will not play a role in the so-called midterm. We're just flying ahead of the next thing. So Monday will be review. I'll talk about the practice test, take any midterm-related questions. Wednesday is the day that the test will be posted online. So we will not have, class will not meet that day. And then the following Monday, the 28th, is Mardi Gras break, so class not meeting then either. So you'll get some time off, I guess, except for midterm and grading it. But yeah. Okay. All right, now everyone's accounted for one way or another. So all semester long, I've been talking about solving Ax equals B by what are called direct methods. Methods such as Gauss elimination, or special cases of like the LDLT factorization or symmetric matrices, or Cholesky decomposition for symmetric positive definite matrices. So in all of these cases, we are working out the solution, the exact solution to Ax equals B, and it will be exact except for the accumulation of round-off error. It's what you would get if you were working out this kind of problem on paper by calculator, for instance. So now that I've spent a lot of time covering F, I can tell you why, in many cases of importance, direct methods are not a good approach to solving Ax equals B. So they're going to totally trash that approach and suggest another. Okay, so first, what if we already know something about the solution? Maybe we already have an approximate solution to Ax equals B. Direct methods do not have any mechanism for taking that information into account. So you go to Gauss elimination and say, hey, I got this. Gauss elimination is like, and? I don't care. So that's unfortunate. And this is something that really does come up. So one of the things that we'll get into later this semester, solving systems of ODEs using implicit time-stepping method, which calls for solving a system of equations. So if that system of equations is linear, you have an Ax equals B problem. And since you're time-stepping, you have your solution from a prior time step that is the right-hand side, and the solution is the solution of the Ax equals B problem is the solution of your ODE system at the next time step. So because you're time stepping, your solution is only changing a little bit in time. So in that case, your previous solution already is a decent approximation of your new solution. Therefore, it serves as an accurate initial guess. And that doesn't help you with a direct method. Right, so that's one reason, but I got more. As I said, the solution obtained by a direct method will be exact except for round-off error. So you can expect generally high accuracy. But what if you don't need high accuracy? It'd be nice if you don't really need that much, if you could therefore get away with less effort. With direct methods, you can't do that. You have to see all the way through. You have nothing. There's no partial solution or something that is only somewhat accurate and then is refined as the algorithm proceeds. You have nothing to work with solution-wise until the very end of the process. And you might think, well, what situations are there where you don't want much accuracy? Pretty much all of mathematical modeling anywhere, because models have uncertainty, and in some cases a lot of uncertainty. And in many cases, there's no point in trying to solve a model exactly if the model itself is flawed. Now, or at least you'd like to be able to do less work to get all the accuracy you could hope for, commensurate with whatever uncertainty you have. So if you have, say 1% uncertainty in your model, then Maybe it's fine to have a solution that's only accurate to 1%. And if you can get that for less than it takes to get full precision, you'd like to do that. Because saving time is certainly essential. So direct methods don't allow this. There's no way to quit early and settle for less. This one has kind of come up already. What if A is sparse? For example, a banded matrix. Pivoting is a problem. Pivoting can destroy sparsity. For Gaussian elimination, even without pivoting, for certain sparse matrices, can destroy sparsity. You have this problem of fill-in. So you have to have some way that of solving A equals B that doesn't lead to this problem. And here's a particularly compelling one. You might not even have A at all, not in the usual way. You think of the conventional way of representing a matrix is just a two-dimensional array of its entries, Aij. But you might not have that on hand. Maybe all you really have is a function that takes as input x, and the output is matrix vector product, A times x. And you can input whatever x you want as a parameter and get A times x, but you don't have the entries to work with, and that makes Gaussian elimination impractical. Now, you could call your function for every standard basis vector as an input and get the entries that way, but again, that's quite impractical. So, if this is your way of representing x, we need to rethink how Ax equals b is solved. Is there a way that relies on matrix vector products instead of elimination for individual entries? So all of these things lead to the need for some very different approach solving Ax equals b. And that's what leads to iterative methods. Now, in chapter 5 of the text, there's this section, 5.1, that deals with stationary iterative methods. That's the only type of iterative method that we're going to cover in this class. So the rest of the chapter, sections 5.2, 5.3, deal with non-stationary methods. And those are covered in a graduate class we have here, a Math 610, that is offered in the spring in odd numbered years. So, learn about those. It's coming up. Okay, in a year. But so, all right. So we're just going to focus on this. So a stationary method is, name comes from being able to write the method in this form, that each new iterate is some function of the previous iterate. And this is called a fixed point iteration. Last semester, I covered fixed point iteration for solving a single nonlinear equation. Later, I will revisit fixed point iteration for a system of nonlinear equations. So, the idea of stationary iterative methods is if I write A as a difference, m minus n, that's called a splitting. So then, I have mx minus nx is equal to b. So I can rewrite ax equals b this way. So x now has to satisfy this equation. And from there, I have an iteration. So I can substitute my previous x into the right side, solve for a new x on the left side, and keep this and use successive substitution to hopefully converge to the exact solution x. So a function g in this case is given by this. So it's m inverse times this right-hand side. So what we want to know is, if we use this kind of iteration to solve ax equals b, how do we know if a fixed point iteration of this kind, x equals 1 equals g of xk, is, how do we know if it's going to converge? Now, of course, this system needs to be solvable without much effort. And we don't want to do, we're trying to avoid direct methods. We certainly don't want to use them here. Now, we could use, if it's a matrix of a nice structure, like a diagonal matrix or a triangular matrix, then this doesn't take much work. So that's essentially gradient in this. That must be easy to evaluate this function for whatever x. So let's consider the question of convergence. I will talk about specific choices of m and n that lead to certain stationary iterative methods, but first, the general case. So here's what we can do. All right. You're gonna copy this here. All right. Okay, so this is a starting point. This is our iteration. So now I'm going to multiply both sides by m inverse. Okay. And then I'm going to subtract the exact solution, x, from both sides. Oh, and I just realized I made a mistake here. M inverse has to be multiplying this whole thing, so I need to put parentheses here. Okay. Now, then what I'm going to do is I'll all right, I'm going to distribute this m inverse through here. Oops, wrong line. Okay. Okay. Now, keep in mind that b is equal to a times x. So I'll go ahead and fill that in here. Okay. But then a is equal to m minus n. So I'll take that into account. Okay. And now I'll take this m inverse and distribute it through here. And what's going to happen is, of course, the m inverse and m will cancel. So now we'll just have identity here. Okay. So now we have, but now if I distribute the x through this whole thing, but now these x's cancel. Now I have m inverse n xk minus m inverse n x, and I end up with this. And I can see it every step of the way. Now what this means is the error after k iterations, Any derivative x by itself refers to the exact solution. That the error after k iterations multiplied by m inverse n is the error after k plus 1 iterations. So we have a clear relationship of consecutive errors. So more generally, if this is the error in the initial guess, then the error after k iterations is just multiplying that initial error by m inverse n k times. So now what I can do is I can find t to be m inverse n. That's called the iteration matrix for a method, which gives us relationship between errors. So now I take the norm of both sides, and if I use a property of matrix norms that I mentioned last time, that the norm of a product is less than or equal to the product of the norms, then I have this relationship between the initial error and the error after k iterations. Now, of course, I want this error to go to 0 as k goes to infinity. So we can see that that will happen if the norm of t is strictly less than 1. So the error will definitely increase, there's definitely decrease in magnitude from one iteration to the next, eventually get arbitrarily close to 0. So what we have here is a sufficient condition that convergence will happen if in whatever norm we choose, like the infinity norm, 1 norm, 2 norm, that the norm of this matrix is less than 1. But I want to point out that it is, while it is a sufficient condition, it is not necessary. So it is possible that the matrix may be, the iteration matrix might have a norm that is greater than or equal to 1. And convergence still occurs. But before I continue, are there any questions?
Is there any specific case for which the norm is greater than or equal to 1 and it still converges? Because I really lost the last line that you said. I lost the last sentence.
Okay. Yes, it is possible that a norm can be greater than or equal to 1 and convergence still happens.
Yeah. Any particular case?
I may not be able to make one off the top of my head, but sorry. Okay. Okay. Now, here is a condition that is necessary and sufficient. That the spectral radius of t, which is the absolute value of the largest eigenvalue of t, that must be less than 1, or convergence will not happen. Recall that this is what the eigenvalues mean, that if tx equals lambda x, lambda is an eigenvalue. And here we have this property that kind of explains why one condition is necessary and sufficient and the other one's merely sufficient. The spectral radius of a matrix is always less than or equal to any induced matrix norm. So what it means is if this is less than 1, then certainly this will be. But maybe this is greater or equal to 1, but spectral radius is still less than 1, in which case convergence still occurs. And to show you why this is true, suppose you have tx equals lambda x. And let's suppose that lambda is the largest eigenvalue of t. So the magnitude of lambda is equal to the spectral radius. So if I take the norms of both sides, then the norm of this side is the spectral radius times the norm of x. The norm of this side is the norm of tx, but that is less than or equal to norm of t times the norm of x. Cancel the norm of x, and you get norm of t is greater or equal to the spectral radius of t. But in general, it can be difficult to determine whether the spectral radius is less than 1 because computing eigenvalues is expensive. Whereas it's relatively easy to compute the, let's say, the one norm or infinity norm of a matrix. So in a situation where you can show that one of those easier to work with norms is less than 1, that's a nice way to prove convergence. Right. Now we have a criterion for convergence that imposes a restriction on the kind of splitting you can have. So if you're going to do splitting, A equals n minus n, then the spectral radius of this matrix needs to be less than 1 for it to work. All right, so any questions about the rest of this convergence analysis before I get into specific methods? Alrighty. The simplest method of all, of stationary kind, is the Jacobi method. So to help me describe these methods, I'm going to use this breakdown of A. So L is what's in the lower triangle below the diagonal. That's why I call it the strictly lower triangular part. The diagonal not included. D is the diagonal part. That consists of diagonal entries of A. And then here we have a strictly upper triangular part, U. Okay, let's jump in. Let's see a typo here in specific. And if I find that exact same typo is in my book, I already know that a lot of mistakes slip through. Oh, I used a different wording in the book, so that mistake anyway is not in there. That's okay. Many other mistakes are, and I keep finding more. And what's unfortunate about it, I'd love to do like a second printing or a second edition where all the mistakes are fixed. Actually, a lot of mistakes did get fixed in the Python edition, but the publisher won't let me until they've sold all the ones they printed. So, well then don't print so much. I knew this wasn't going to be a bestseller. What the hell were you thinking? Sorry. It's a little salty about that. Okay. Sorry for language. Like I said, salty. Okay. So, with this splitting of A, I can describe the splitting that defines the Jacobi method, where the matrix M is just the diagonal part. And then everything else goes into n. And keep in mind, A is m minus n, which is why we have a minus here. So that m minus n will be d plus L plus U, which is A. So, as I mentioned before, whatever system you have to solve involving m must be easy. And can't get any easier than this, solving a diagonal system. So I can write the iteration this way. So the new x is equal to d inverse times b minus L plus U times the old x. And here's the same iteration written in component by component form. So each component I of the new x is 1 over the corresponding diagonal entry, and then each component of this expression is given here, so bi minus the ith element of this matrix vector product, really multiplying A times x, except for the diagonal entry, that's not included, so that's why I have j not equal to I here. Oh, we have everything else. So you could use this in your code. So to implement the Jacobi method, you can use this formula within a for loop of I going from 1 to n. At least if you're in a setting where you're allowed to use for loops. Right, that was a COS 702 reference. So. All right. So once you have an initial guess, and an initial guess can always just be x equals 0, unless you have some other unless you have some knowledge about the problem that gives you some approximate solution. So you can have a outer loop that computes each component. That's the inner loop. The outer loop is for managing the iterations. So your outer loop is over k, and k is going to keep counting up from 0, 1, 2 until convergence occurs. So for example, you can check the difference between successive iterators, take the norm of the difference, and stop when the iteration is less than some tolerance epsilon. Inside this loop is where you carry all of this out.
I have a question about that.
Yeah.
Does that mean we only have to actually store the previous iteration?
Yeah.
And then we can just keep rewriting it over and over again?
Yes.
Okay.
Yeah, but you definitely don't need to store all the iterations. Yeah. Ooh.
That would be
A lot.
a lot, yeah.
Yeah, especially for large matrix.
Exactly.
Okay.
Who's gonna pay?
So that's what Jacobi, how Jacobi method works. Or is there any questions about the Jacobi method before I talk about a modification of it? Okay. Now, one thing that's worth pointing out about the Jacobi method is so here it's assumed that all the components of each iterator are being computed in order. So first component, second component, all the way to the end component. Now, so let's suppose we've gone pretty far down the list. Like, let's say we're solving a 100 by 100 system. And here we're down to component 50, so I equals 50. So that means we've already computed components 1 through 49 of the new xk plus 1. But then we compute this sum, and when j is going from 1 to 49, we're using the old x values, when we already have the new ones. So this sum is not using the most up-to-date information we have about x. So what if we were to do that? That leads to the Gauss-Seidel method. So what I've done with Jacobi, this is Jacobi again, but I've broken the sum up into two sums for j less than I and j greater than I. So here we're using components of xk when the corresponding components of xk plus 1 are already known because we're going in order. So we just change this one to be xk plus 1. Now we're using the most up-to-date information that we have. Whereas here, we don't have these components of xk plus 1 yet, so we have to stick with xk here. So that's it. That's the only change. And if we try to write this in matrix vector form, then we would have this, where L is now multiplying xk plus 1 rather than xk, whereas U is still multiplying xk. But then what I can do is okay. If I multiply both sides by d, okay, I'm going to show you how I got this. Okay, so multiply both sides of this equation by d. So I have a d here, and this is gone. Dang it. They don't need those square brackets either. And then I'll take the minus L xk plus 1 term and move it to the left side, okay, and now I'll factor out xk plus 1 on the left side, factor it out to the right. Okay, and then I multiply both sides on the left by d plus L inverse, and now I have this iteration. So this is your M. So M is d plus L, and then N is the rest of A, which in this case is just minus U. So that's the Gauss-Seidel method in matrix form. Now, which method is better? It's not so clear-cut. There are certain situations where it can be proven Gauss-Seidel works far better than converges far more rapidly than Jacobi, but that's not true in general. Also, because of the way Gauss-Seidel is written here, I have to, in order to compute component I have to, of a new x, I need components 1 through I minus 1 of a new x. In other words, I cannot parallelize. Whereas with Jacobi, you may be using old information, but that independence of the computation for each component means that all the components of a new x can be computed in parallel. So there's definitely a trade-off here. What's kind of interesting, it seems paradoxical, but really it's not. Considering that this is Jacobi, this is Gauss-Seidel, you can clearly see that the amount of computation required for two methods per iteration is exactly the same. It's the exact same computations being performed, it's just that they're being applied to different components of different x's. But the actual work involved, the amount of work per iteration is the same. And yet, when you look at the matrix vector description, Jacobi, you're solving a diagonal system, which involves only n divisions. Whereas with Gauss-Seidel, you're solving a lower triangular system, which involves n squared operations. And yet the work is the same. Now, it can seem kind of paradoxical, except in Jacobi, you're doing two of these matrix vector products that involve order n squared work. Whereas in Gauss-Seidel, you're only doing one of them. So really, in effect, one of those matrix vector products in Jacobi is shifted to this part. So that's why you can see that even in matrix vector format, the amount of work involved is the same. So questions about Gauss-Seidel?
How do we decide what to use?
Well, I guess one consideration is your computer architecture. If you have multiple processes for your environment, then you might want to use Jacobi. And you can check for certain classes of matrices. Do I have a commentary on that here? Oh, I don't. Okay, I'll also talk about that later. Okay. I have to check something here with text that for some reason is not in my notes. Or something I might have deferred to homework problems. Actually, I should check which homework problems I've assigned for this. And you only need to do it for a while, but okay. 1 through 4, 6, 8, 9. Okay. I do have one more iterative method to talk about, so I'll deal with that first, and then I'll share some other information. So here's Gauss-Seidel again, except written a little differently. Because everything you see here is from the original Gauss-Seidel, except I've thrown in this term here, which is offset by this term here. So now it's looking like xk plus 1 is equal to xk plus some correction. So you can think of this as how you change the old x to get the new x in Gauss-Seidel. So suppose I want to take a step from xk to xk plus 1 that goes in the same direction, but I want to go further in that direction by multiplying this whole part by a parameter omega. That's called a relaxation parameter. So when I do that, if I multiply both sides by aii, then this is what I have for my iterative method. In a matrix form, it becomes this. So now I have a much different splitting, and I'm solving this lower triangular system. Instead of d plus L, it's d plus omega L, where omega is my relaxation parameter. And then I have this 1 minus omega d over here. Notice also that b is multiplied by omega. And so this is called the method of successive over relaxation, or just SOR. And it can be shown that a necessary condition for convergence is that the parameter omega is chosen between 0 and 2. Really, you think of omega greater than 1 as being over relaxation, and omega between 0 and 1 being like under relaxation. Generally, best results are achieved when you choose omega to be between 1 and 2, but you can choose it to be between 0 and 1 and still get convergence. And if omega equals 1, it just reduces to Gauss-Seidel again.
Excuse me, sir.
Yeah.
Does in practice it matters how rapidly it converges?
Sorry, what?
In practice, does it matter how rapidly it converges?
It can. Yeah, because, for example, I've seen some cases where, because it's a spectral radius of t that determines convergence. I've seen some cases where changing the choice of iterative method ends up taking the spectral radius, say for Jacobi, and squaring it to get the spectral radius for Gauss-Seidel. So that's going to be much more rapid convergence. So, yeah, that matters. Okay. Well, yeah, you never know. Sometimes it seems to make only a small difference, but yeah. Okay. Now, to explain why omega must be between 0 and 2. Here's the iteration matrix. Now, I want to take a determinant of this whole thing. So that would be the determinant of this times the determinant of this. But both of these matrices are triangular, so those determinants are easy to get. Here, the determinant is just 1 over the product of all the diagonal entries. That's what we have here. And here too, this is an upper triangular matrix. So again, we're multiplying the diagonal entries, and we get this. Then we have AII inverse and AII canceling out. So this is the determinant, 1 minus omega to the n. But the determinant is also the product of all the eigenvalues. So and also all the eigenvalues individually have to be less than 1. So including the largest of these. So we can think of this. So this determinant, okay, which the product of the eigenvalues is less. Whoops, dang it, less than or equal to the spectral radius raised to the n power. Since that's the largest eigenvalue. So by setting this less than or equal to this, then we have this inequality. And this has to be less than 1 for convergence. Therefore, omega must be strictly between 0 and 2 for convergence to occur. Yeah, SOR was someone's PhD, which I guess today makes every numerical analysis PhD student feel like an underachieving schlub, including me. And yeah, you can actually obtain, you can actually look up his dissertation, and thankfully typeset in a modern manner, so that, because if you look at old math, like from around this time period, LaTeX wasn't a thing yet, and so we're using like an ordinary typewriter and still trying to figure out how to do the math symbols. I think some are often were hand drawn in. It really is painful to try to read. So thankfully, someone took the time to.
This is a new copy. I'm trying to find it.
And the thing is, so I spent some time taking a look at the dissertation. I'm looking at one of the proofs. It didn't seem right, to be honest. But of course, I have no room to talk when it comes to mistakes in one's dissertation. I'm aware of some embarrassing ones that have been repaired since then in my publications. But yeah, so. Yeah, so this is so these three, Jacobi, Gauss-Seidel, and SOR, are the best known stationary iterative methods. There is a variation of SOR called SSOR, so symmetric successive over relaxation, that's designed for symmetric matrices. I do some more convergence stuff I want to talk about with these methods, but first, questions.
So, for picking like between those two, we're not, at least I don't think that we're guaranteed invertibility of like D plus L always.
Okay.
But I could very well be wrong on that. So is that one of like?
Okay. So, yeah. All right. Okay. So one drawback right off the bat of these methods is that the diagonal entries must all be non-zero.
Yeah, so if the diagonals are non-zero, then we would be guaranteed invertibility for
Yes, you
L
will.
plus D.
Yes.
Okay. So is that for like all of the methods that we're learning? Is that the diagonals have to be non-zero?
Yeah, but that is required for these methods. Yeah.
Now, for one of the homework questions, it says that we need to find n, like for the number 8.
Oh, in this section?
Yes.
Okay, actually, I want to pull a book up anyway, so 1 second. Problem 8.
Yes. Yeah, so like the transition equation at the very top.
Yeah.
It confuses me why that doesn't tell us the answer for 8. Now your hint says they are not the matrices D plus omega L and the other one.
Yeah.
Isn't the transition matrix an inverse times n?
Okay. To see why this equation is not exactly the same form as 5.1. Okay, so just so everyone else can see. By equation 5.1, I mean the general iteration. Look at the b term. So you have to get the equation in a form where the last term is b by itself. Yeah. So yeah, there isn't much to this problem, but yeah, this is it. One of the problems that I assigned in this section, number 3, is about proving that for a certain category of matrices, Jacobi is guaranteed to converge. Now, the matrix is strictly row diagonally dominant, meaning the diagonal entry in each row is larger magnitude than the sum of magnitudes of all off-diagonal entries in that row. And this kind of matrix comes up, for example, solving differential equations. Based on finite differences. So this is an important class of matrices that does come up in certain applications. And keep in mind what I said earlier, it can be difficult to determine whether the spectral radius of an iteration matrix is less than 1, but it can be easier to figure out if the norm is less than 1. Because all we're looking for is efficiency here. Another category for convergence. And I think it's not for a problem that I assigned. Oh, okay. But one thing also Seidel mentioned here, if the matrix A is symmetric, positive, definite, and tridiagonal, the optimal omega is known. It can be proven that this maximizes the speed of convergence. In terms of the spectral radius for the Jacobi method applied to the same matrix. Another thing I mentioned, okay. I have these problems at the end of each chapter which I never assigned. Okay. If A is 2 by 2, symmetric, positive, definite, spectral radius of Gauss-Seidel is spectral radius of Jacobi squared. Now, of course, it's a 2 by 2 system, but in this case, Gauss-Seidel is much faster.
That's what you said just a second ago.
Sorry, what?
That's what you said a minute
Yes. Okay. I have something here I want to mention about. Where did I put it? Okay. If A is symmetric, positive, definite, then SOR is guaranteed to converge. And since Gauss-Seidel is just SOR with omega equal 1, then Gauss-Seidel will converge for symmetric, positive, definite matrices as well. If I remember correctly, it is not a guarantee convergence for, I think Jacobi, there's an additional assumption required besides symmetric, positive, definite to guarantee convergence. And I'm totally talking off the top of my head, but I think I recall reading that, okay, you're proving that Jacobi converges for strictly row diagonally dominant. I believe Gauss-Seidel will as well. Something I should know off the top of my head, but it's currently escaping me. You know what? I'm going to cheat. Let's find out. Okay, yes, alright, so I remember that correctly. That it's diagonally dominant, that Gauss-Seidel does converge. Whereas for the Jacobi method, okay. Yeah, so diagonally dominant. Okay, yep. It is not guaranteed to converge for every symmetric positive definite matrix. And I remember reading somewhere that some other condition had to be satisfied. I don't believe that's mentioned here. Oh. Okay, this is the variation of the weighted Jacobi method that does converge in the symmetric positive definite case. Okay. So at least I remember correctly. You never know. That's something else working with the second edition, I guess. Okay, so these are some of the simplest iterative methods. Okay, well, do we have any other questions, homework questions, midterm questions? Which you should bring with you on Monday. Okay, it's going good.